From the outside, it looks like a warehouse. Steel walls, massive doors, no ornament, no drama. But inside the rocket factory operated by SpaceX, something extraordinary is happening, quietly, repeatedly, and with absolute intent. This is not a factory built to impress visitors. It is built to solve a problem humanity has struggled with for decades. How do you leave Earth and come back? The answer begins with materials. Sheets of aluminum and stainless steel arrive in precise batches. These are not ordinary metals. Each alloy is chosen for strength, weight, heat resistance, and cost. Spaceflight is unforgiving. Every gram matters. Every flaw multiplies at launch. Inside fabrication halls, massive cylindrical sections begin to take shape. Metal is rolled into towering tubes, rocket bodies forming vertically, not horizontally like aircraft. This choice is deliberate. Rockets do not fly sideways. They are born standing up. Robotic welding arms move methodically along the seams. Their arcs glow white-hot as they fuse metal together in continuous lines. Unlike traditional segmented welds, these seams are smooth and uninterrupted. Fewer joints, fewer weaknesses. Lasers scan every weld in real time. If a seam is even slightly imperfect, it is flagged immediately. The process does not continue, hoping it will hold. Space does not reward hope. Above the factory floor, cranes lift massive rocket tanks effortlessly. What looks slow is actually controlled. Momentum is managed. Precision is absolute. One uncontrolled movement could destroy months of work. Inside these tanks, internal structures are installed. Baffles, reinforcements, and fuel channels designed to manage liquid oxygen and rocket fuel during violent ascent. These fluids behave like living things under acceleration, sloshing and surging. The rocket must control chaos. While the body is being formed, another section of the factory focuses on propulsion, the heart of the rocket. Rocket engines are assembled piece by piece. Turbopumps, injectors, combustion chambers, each built to withstand temperatures hotter than molten lava and pressures that crush steel. Nothing here is oversized for safety. Everything is sized for efficiency. Engines are not just assembled. They are measured into existence. Sensors confirm tolerances smaller than a human hair. Software monitors every step. Torque values are exact. Deviations are not adjusted later. They are rejected now. Once assembled, engines are mounted onto thrust structures. Engine bells reflect factory lights like mirrors. They are beautiful, but beauty is incidental. These engines must survive fire. Avionics come next. Flight computers, redundant, shielded, and hardened against radiation, are installed deep within protective bays. Wiring harnesses snake through the rocket's interior like nerves. Each path is intentional, each connector locked and verified. These computers will make decisions faster than humans ever could. They will guide the rocket through atmosphere, vacuum, and re-entry. Then comes one of the most radical ideas in modern aerospace: reusability. Landing legs are assembled and attached. Grid fins, metal lattices used to steer the rocket during descent, are mounted precisely. Heat shield tiles are prepared and installed in patterns that distribute thermal stress evenly. This rocket is not designed to die. It is designed to return. Before anything flies, everything is tested. Rocket stages enter environmental chambers that simulate the brutality of launch in space. Vibration tables shake them violently, replicating the forces of ascent. Thermal vacuum chambers remove air and alter temperatures, mimicking orbit. If something fails here, it has already saved lives later. Engines are moved to test stands for static fires. Fuel lines pressurize. Valves open. Ignition begins. For a few seconds, the engine roars, held firmly in place while it unleashes controlled destruction. Flames blast against deflectors. Sensors capture thousands of data points per second. Then silence. Cooling metal ticks softly. Data flows. Engineers do not cheer. They analyze. If numbers are wrong, the engine does not fly. If numbers are right, the engine earns its place. Once cleared, rocket stages are prepared for integration. Sections are stacked vertically, forming something unmistakable now. A launch vehicle. Standing beneath it, humans appear small. Not because the rocket is intimidating, but because scale matters here. This machine is designed to leave a planet. But even now, the factory is not done. Every step taken to build this rocket feeds information back into the system. Designs evolve quietly. Materials change subtly. Processes refine themselves. This factory is not repeating history. It is rewriting it. And the rocket is only halfway finished. Thumbs up if you're enjoying this deep look inside how rockets are really built. Tap the like button. Once a rocket leaves the main assembly hall, its journey is no longer theoretical. It becomes operational. Inside SpaceX, there is a clear boundary between building something and trusting it. Crossing that boundary requires proof, layer by layer, system by system. The completed rocket stage is transported slowly from the factory floor to an integration facility. Massive transporters carry it upright, rolling carefully across reinforced paths. This is not spectacle. It is necessity. Rockets are designed to stand vertical, and keeping them that way reduces stress and risk. Inside the integration tower, the rocket begins to resemble its final form. The first stage is secured to a launch stand. Structural locks engage. Sensors confirm alignment. The second stage is lifted overhead and lowered precisely into position. Mechanical couplings connect fuel lines, electrical systems, and data interfaces in one controlled sequence. This moment matters. From here on, the rocket is no longer a collection of parts. It is a system. Payload adapters are installed next. These structures will connect satellites, cargo, or crew capsules to the rocket. Each mission is different, so this step is customized carefully. No assumptions are allowed. What works for one payload may fail for another. The payload itself is handled in clean, controlled environments. Satellites are sealed inside protective fairings, two curved shells designed to shield delicate instruments from the violence of ascent. Acoustic insulation lines the interior, dampening sound levels that could otherwise destroy sensitive equipment. Once closed, the fairings form a smooth aerodynamic nose. Nothing inside is visible anymore. The rocket now enters a phase of testing that does not involve fire, but is just as intense. Avionics systems run full mission simulations. The flight computer replays entire launches digitally. From engine ignition to orbital insertion, every step is tested virtually. If something does not behave exactly as expected, the system flags it instantly. Fuel systems undergo final pressure verification. Valves open and close. Tanks are chilled to cryogenic temperatures. Vapor clouds briefly form as liquid oxygen and fuel flow through the system. The rocket begins to look alive. Outside, the launch site waits. When the time comes, the fully integrated rocket is rolled out to the pad. This journey is slow, deliberate, and silent. The rocket does not rush toward space. It is escorted. At the launch pad, the rocket is raised upright. Support structures connect. Umbilical lines attach, providing power, data, and environmental control. The rocket stands alone now, but it is not isolated. Thousands of systems are watching it. Launch rehearsal begins. Countdowns are simulated again and again. Go/no-go polls appear on screens. Every subsystem must report green. Range safety systems are armed and verified. Weather data streams in continuously. On launch day, fueling begins. Cryogenic propellants flow into the rocket at temperatures colder than anything naturally found on Earth. The metal exterior begins to frost. Sensors track pressure, temperature, and flow rate in real time. There is no margin for error here. As fueling completes, the rocket enters a state of readiness. The launch tower slowly retracts. The vehicle is now self-supported. Engines ignite in sequence. A deep, controlled rumble builds beneath the rocket. Thrust rises. The hold-down clamps release, and the rocket moves. Liftoff is violent, loud, and brief. Within seconds, the rocket is climbing faster than sound, punching through atmosphere on a column of fire. Cameras track it upward. Telemetry floods control centers. Stage 1 engines throttle carefully as the rocket accelerates. At the planned moment, the first stage shuts down and separates. The second stage ignites, pushing the payload toward orbit. But the story does not end there. The first stage flips in midair, guided by thrusters and grid fins. It re-enters Earth's atmosphere at hypersonic speeds, wrapped in plasma. Heat builds, stress peaks. This is where most rockets would die. Instead, engines relight. A landing burn slows the descent. The booster touches down, either on land or on a drone ship at sea with meters to spare. Reusability becomes reality. Back in orbit, the second stage deploys the payload. Fairings separate cleanly, floating away as Earth curves below. The mission objective is complete, but the factory is still involved. Telemetry from the flight streams back immediately. Engine performance, structural loads, thermal behavior, everything is recorded. Recovered boosters return to port. They are transported back to inspection facilities where engineers examine them closely. Heat shield tiles are checked. Engines are cleaned and tested. Structural scans search for microfractures. If a component passes, it is cleared for reuse. If not, it teaches the system something new. Flight data feeds directly into design and manufacturing updates. Welding techniques adjust. Materials evolve. Procedures refine themselves. The next rocket is already better. This is how the factory extends beyond its walls. It does not stop at the launch pad. It reaches into orbit and back again. Bell if you want more cinematic deep dives into how the world's most advanced technology is built. Subscribe. The final session is coming next. When a rocket returns from space and lands upright, something profound has already changed. Not just for the mission, but for the factory that built it. Inside SpaceX, flight is not the end of manufacturing. It is feedback. Every launch, every landing, every re-entry is treated as a data-rich extension of the factory floor. This is where SpaceX departs completely from traditional aerospace thinking. Most factories ship a product and move on. This factory waits for it to come back. Recovered boosters arrive at inspection facilities coated in soot and scars from re-entry. They look used, but appearance is misleading. Engineers and automated systems scan them thoroughly. Ultrasound checks for microfractures, thermal analysis evaluates heat stress, and structural sensors verify load history. What matters is not how the rocket looks. What matters is what it learned. Engines are removed, cleaned, and tested. Some fly again quickly. Others are retired early because they revealed something important. Every decision feeds into future builds. Nothing is wasted. This feedback loop accelerates improvement at a pace aerospace had never seen before. Instead of waiting years between design revisions, SpaceX updates continuously. Welding paths change. Materials improve. Assembly sequences simplify. The factory evolves with every flight. But SpaceX does not stop at improving existing rockets. Inside massive bays, something larger is taking shape. Starship. Unlike previous rockets, Starship is built almost entirely from stainless steel. This choice shocked the aerospace world. Stainless steel is heavier than carbon composites, but it is cheaper, stronger at high temperatures, and easier to manufacture. And crucially, easier to repair. Starship sections are welded rapidly, stacked vertically, and tested aggressively. Heat shield tiles are installed in hexagonal patterns designed to survive repeated atmospheric entry. Engines cluster beneath the vehicle in numbers never attempted before. This is not a launch vehicle designed for occasional missions. It is designed for frequency. Starship represents a shift in how factories think about spaceflight. Not as rare events, but as operations. Flights measured in hundreds, then thousands. To support this, the factory itself becomes more autonomous. Robots self-diagnose where maintenance occurs before failures happen. AI systems schedule production, balance energy loads, and optimize material flow. Even energy usage is integrated. Solar arrays feed power into factory systems. Batteries stabilize demand. Waste heat is recovered and reused. Sustainability is not a side goal. It is efficiency applied at planetary scale. But perhaps the most important system is invisible. Data. Every rocket, every engine, Every component generates information that feeds directly into design models. Digital twins simulate full life cycles before parts are built. Manufacturing parameters update automatically based on real-world performance. This creates a closed loop between design, manufacturing, flight, and reuse. A rocket launched today improves a rocket not yet built. And this loop extends beyond Earth. SpaceX's long-term vision is not just orbit. It is Mars, lunar bases, deep space logistics. None of this is possible with disposable systems. Factories that build once cannot support civilizations. Factories that learn might. Starship production lines are designed with this future in mind. Larger components, faster welding, simplified structures, rapid iteration. Failures are expected and welcomed early. In this environment, failure is not a headline. It is a teacher. The factory does not fear explosions during testing. It studies them. It does not avoid risk. It contains it, measures it, and uses it. This mindset is what allows progress at this speed. As night falls, factory lights remain on. Robots clean work areas. Systems recalibrate. Simulation models update using the day's flight data. By morning, production resumes. Smarter, more efficient, closer to something humanity has never done before. This factory is not just building rockets. It is building capability. The capability to launch cheaply, to land reliably, to reuse relentlessly, to scale spaceflight until it becomes infrastructure, not spectacle. If rockets once symbolized ambition, this factory symbolizes discipline. Not dreams of the future, but preparation for it. And somewhere inside these steel walls, the next rocket is already learning how to leave Earth and come back better than the last. Speech Balloon, now tell me in the comments, which future factory or space company should we go inside next?